Hi, welcome to the second lecture on corrosion of embedded metal. In this we will be covering carbonation-induced corrosion and chloride-induced corrosion. This is the outline of the module on corrosion of embedded metal, where we will have 5 lectures. First we already covered as lecture 1, which is mainly on significance and fundamentals of corrosion, and then today we will be covering carbonation-induced corrosion and chloride-induced corrosion, and 2 lectures on this and 1 lecture on corrosion in prestressed concrete. So, just a quick recap on the lecture 1, where we covered basics of corrosion. When we put the steel in concrete, we found that there is something called passive film forms, which prevents the corrosion of the steel further. And we also looked at 4 components of the electrochemical cell, where you have an anode, and anode where the region the corroding region is defined as the anode, then the other region on the metal which functions like a cathode, and then a connection or a ionic and electronic conductor. The metal itself plays or functions like an electronic conductor, and the concrete will function like an ionic conductor or any solution to which the metal is exposed to. And the anodic reaction which we are mainly talking about is this, where you get Fe2 plus and 2 electron discharge, and the cathodic reaction is this, where hydroxide ions are formed in presence of oxygen and moisture and the electrons which is released from the anode. Now, let us look at how carbonation influences the life of the concrete structures. What you are seeing here is a schematic of various phases of concrete structure, like of service life. What you see here is the blue region indicates the initiation phase. Essentially, we can say that is the phase where there is no corrosion happening, because corrosion starts to occur at this time, or the onset of corrosion is right here. So, from here to here there is no corrosion happening. Now, what is happening during this initiation phase is that the carbon dioxide in the atmosphere, it will try to penetrate into the concrete and react with the concrete and try to reduce the pH of the concrete. And when the pH of the concrete in this region, like the near the steel surface, it reaches a value of about 0.9, the steel will starts corroding, and that is at this point here, this point in time. The pH is about 0.9, and then the steel will start corroding at that time. Now, beyond that point, the steel will continue to corrode, and it will lead to cracking of the concrete or further corrosion, and then we call that phase as propagation phase. This is here propagation phase. Now, the structure will continue to corrode, or the steel will continue to corrode and reach a particular level where you have to start doing the repair, or the structural safety may be a concern. So, we start repairing the structure, and that starts from here. Now, and how do we achieve this is by looking at different factors which affect the carbonation and carbonation-induced corrosion, and we have to look at various factors. It is not just one factor to be looked at, it should be various factors. All the factors influencing carbonation and carbonation-induced corrosion should be looked at, and then only we should say, okay, a particular system will actually have a long life. I want to correct this thing here, this it is not actually chloride, please make a change, it is CO2. So, carbon dioxide concentration at the surface of the concrete. Now, let us look at some typical locations where carbonation can happen in a typical type of structures where carbonation can happen. This is a bridge it indicates very clearly you have a lot of vehicles here. So, the near surface of the concrete elements can actually have very high concentration of CO2 because of all the exhaust gas from these vehicles. This level could be much larger than what you would actually see as atmospheric CO2 concentration. So, these kind of structures can experience carbonation, especially when the humidity, relative humidity is about 60 to 70%. And you might see that there are several locations where you have, if you have rain or humidity is very high, then if it is very high like beyond 70%, you may not see that high carbonation, but 60 to 70 is a very very bad for the structure when you talk about carbonation induced corrosion. And that is also a reason for corrosion in the coastal region. Usually we think that in the coastal region we see only chloride induced corrosion, but that is not usually the case. Carbonation also can happen, but most cases you will see that chloride induced corrosion will be the governing thing, but carbonation can also happen. Do not neglect carbonation when you talk about coastal regions. Other type of structure where carbonation, which I look, this is typically on railway railway platforms you will see, or railway stations you will see this kind of fences, where you can see that this, you look carefully here, you have a lot of these vertical cracks along these different vertical members exactly through the center of it. Actually these members, if you look at the cross section of these vertical members, it will look something like this, and what is happening is this portion here is actually very porous mortar which they use for making these fences, even if it is concrete, but the aggregate size would be very small. And what you will see is they are very porous in nature, and the steel inside, there will be one rebar which is inside this fence that will corrode, expand, and it will lead to cracking. We looked at in the last lecture that once the steel starts corroding, there is about 6 times volumetric expansion which will lead to corrosion cracks like this. That is what you see these cracks. So basically this point which you are looking at is here or here or here or here. Okay, let us now look at what is the mechanism of carbonation and carbonation induced corrosion. Here I already explained this, but let me explain once more. As you see here, the CO2 can penetrate into the concrete and then it will react with the calcium hydroxide which is present in the concrete, and in this reaction what is happening is this calcium hydroxide which gets consumed, and if the consumption of calcium hydroxide is too much, then what will happen is it will eventually reduce the pH of the concrete. Of course, concrete has a high buffering capacity. However, there may be a case when a lot of reaction happen, then the pH will reduce, which will, like if the CO2 penetrates and reaches up to this level, the pH of the concrete around the steel reinforcement, if the pH becomes about 9, then you can see that the steel will start corroding. This is a more detailed reactions, intermediate reactions on this mechanism. What first happens is carbon dioxide will penetrate into the concrete, react with the moisture, and it will form carbonic acid, which then reacts with the calcium hydroxide. So eventually in this reaction we have consumption of OH minus is happening, and then at a later stage what will happen is CSH or the calcium silicate hydrate will also liberate calcium oxide, and it will also lead to formation of calcium carbonate. So if effectively you have a significant reduction in the pH of the concrete, that is what is written here, significant reduction in the pH which leads to a case where steel is no longer protective. Now let us look at how this carbonation depth can be measured by using a simple test. Like if you remember earlier college time, where you might have used in the chemistry lab, you might have used phenolphthalein indicator to see a change in the pH. So as in the same way we can spray this phenolphthalein indicator onto the concrete surface, and depending on the pH of the concrete surface it will change the color. For example, here this colorless region, or when this solution is sprayed there is no change in the color, this region indicate that pH of that region is greater than 9, and whereas this its pH is less than 9, and whereas in this region the pH is greater than 9. That means the region with pH less than 9 is highly carbonated, and the region with pH greater than 9 is uncarbonated region. Of course, you can also think like CO2 penetrates from outside to inside. So, of course, the outer or the peripheral region will be carbonated before the interior. Now, this is a test how it will really look like if you have if you take a core from the concrete structure. You can see here there is a rebar here, you can see. Actually, this rebar, by looking at this image, I can say that this rebar is going to start corroding very soon, because the region the CO2 penetrates from here, CO2 penetrates from the top down, and what you can very clearly see is this line here, just the carbonation front is almost reaching the steel surface. Now, if you wait for longer time, you will see that this region also becomes colorless, and that means the steel is gets exposed to carbonated concrete and pH is low. So, it will start corroding. However, I want to mention one thing, very important thing here. We should never extract a core from a structure where we should never extract a core with rebar. If you should do a proper check whether there is any rebar present in the area where you are going to core. Before that, you should, it is very important to check. You should not damage the structure, because by cutting the rebar you are actually damaging the structure, which should not be done. So, it is very important to check whether there is a rebar before you actually take a core. Now, this is a photograph of some experiments which we are doing here. What we are doing here is looking at how the exposure condition influences the rate of carbonation in a particular concrete. But actually we have similar kind of specimens inside this shelter also. And what we found is, when you have sheltered specimens or the specimens where it is not directly exposed to the sunlight, you can actually have more carbonation. So, in other words, if I relate this to, so in this case this has more this specimens inside this shelter will have more carbonation than these specimens which is exposed directly to sunlight. Or if I relate that to a real structure, so imagine that this particular bridge is actually using all the elements might have same concrete. However, I would expect that the region here will have more carbonation than this region over here, because this is most of the time it is exposed to the direct sunlight. So, you have very low internal humidity over there, whereas in this case you might have once it is humidity, it is very difficult to change the relative humidity here, and also so that leads to more carbonation in this region than in this region. Now, let us look at chloride induced corrosion. What happens in that case? So, what is happening is very similar to the carbonation induced corrosion. What you will see is there is also an initiation phase which is indicated by this blue region, and you have, let us say you have these are the factors which influence. You have chloride surface chloride concentration, and then you also have the rate diffusion coefficient which indicates the rate of penetration of chloride into the concrete, and there is also another term which we call decay constant. In other words, this is very important when you talk about new type of concretes, and because which keep on hydrating for longer period of time, and then you might see that the diffusion coefficient keeps changing as a function of time. So, we have to consider that also when we talk about service life estimation and all that. In other words, you should not just look at 28-day diffusion coefficient and then compare different concretes. It is not the right way to do. More details on this we will cover towards the end of the course when we talk about service life estimation. Okay. Now, there is a very important parameter which we say chloride threshold. which is the amount of chloride required to initiate the corrosion when we talk about chloride induced corrosion. Now, what is happening here is the corrosion initiates at this point. So, the chloride penetrates through the concrete cover, reaches the steel surface, and it's keep on building up at this steel surface over here. And when the chloride content over there reaches the chloride threshold value, then you can say that this corrosion will initiate at that point of time. Now, the time from the beginning until that point is what we call time from the beginning until this point, we can say it is corrosion initiation time, and beyond that we can say it is corrosion propagation period. Again, as we discussed in the carbonation induced corrosion case, we start doing the repair work right here. So, this is where we start doing our repair phase starts here. Now, we have to see how to build durable structures, which is mainly a phase from here to here, or some people say it is up to here, and then you have propagation phase, and for we also have to worry about durable this time here, time for for durable repair. That is also very important to look at, how to ensure that the repair which we do is also durable, which is main focus of this course. We have to really look at synergistic effects of chloride diffusion coefficient, chloride threshold, and chloride surface chloride concentration. How all these have to be looked at, and the service life should be estimated, and then only we should decide which material combination or system should be selected. We should not make comparison just based on diffusion coefficient or just based on chloride threshold. The synergistic effect on service life should be considered. Now, let us look at where we usually see chloride induced corrosion. I mean, we see it in many places. I am going to show you some examples where it is more prominent. First of all, it is sea water or marine conditions, where whatever structure which is exposed to either sea water, may be in direct contact with sea water or very close proximity to the sea water, you can have chloride induced corrosion. So, here this is a concrete pier or a pile where you can see significant corrosion at that wet dry region. Here also splash zone, all this you can see a lot of corrosion on all these elements, because you have very rich rich chloride environment. And here also it is again a port structure, you can see a lot of corrosion here. In fact, this particular structure there is a lot of repair also being done, but we found that those repair also were not lasting long enough. So, a lot of repeated repairs have been done on that particular structure. This is a view of a particular bridge just below from below, and this bridge is located right above a water body. And this is an interesting thing where people have tried to actually protect, how to prevent chloride induced corrosion. You can see a jacket placed right around the columns near the splash zone, which helps which prevents this particular problem from happening. This is another you can see this as a temple view actually here. This is very close to the sea, and you can see the rebars inside this elements are also severely corroding. And actually most of these type of architectural features, that those elements will be made out of very rich cement rich concretes, which actually should not be a practice. Anyway, just wanted to mention that less the cement, better the concrete will be. Okay. Now, some other locations we talked about, where we talk about direct contact with the sea water or very close to the sea water. And if you move a little bit away from the seashore, again you can have a lot of airborne chlorides, where this is one building where you can see very severe corrosion, cracking. This is also very close to the seashore. This is another building again facing seashore. You can see a lot of areas with a lot of patchwork happening. You can see all this. And then this is a close up of over this one of the sunshade in this building. You can see this very severe corrosion. And another thing to mention is where, see, as I mentioned earlier, moisture and oxygen are essential for corrosion to happen, especially when we talk about reinforced concrete elements. Now, here you can see drain pipe over here, and usually what we do is we do not give any space around the drain pipe. When we drill a hole through a concrete element, we pack all that region with mortar. So, what is happening is this drain pipe does not have any space to move, and which leads to breaking of this or cracking of this drain pipe, especially if it is a very brittle material, made of a brittle material. So, we should think about those aspects also and try to provide some cushion over here, so that that pipe will not be broken when there is some movement, and in that way we can actually prevent this moisture ingress into the concrete around or moisture attack of the concrete around the drain pipes. Now, other example which I would like to mention is a lot of these pedestrian highways or elevated structures. We usually walk on top of this, and then we see that everything is fine. You see a nice tiled flooring and everything is fine, but if you just look below the tiles, this is how that looks like. This is from the same structure, and this is also located very close to the seashore. You can see how severely corroded these elements are. So, just by putting a cosmetic, I would say that this tiling is just a cosmetic thing. It is not really addressing the root cause of this problem here. So, we should be very careful, just by look is not important. You have to also address the core concrete, which really gives a strength to the structural element. This is another example of a localized corrosion, localized chloride attack. This is a building. This shows a picture of a building or a chemical plant. Actually, this region over here, it uses hydrochloric acid for the production of these chemicals here, and because of that HCl rich or chloride rich environment, you can see the beams over here has severe cracking here, and unfortunately this is not at all a safe practice, but I had this photo, so I thought of sharing this in the class. You can see this propping, just prop support. It is not really a safe practice. You should replace the beam or do a proper protection, and so there are many cases where such unsafe practices do happen. And you can see even this tank over here, it is also corroding, you can see that. So, the safety of the workers of who are working here is really not really considered in a good manner, I would say. So, that is something which we have to stop from doing. And you can here also you can see a lot of cracks all along the structural elements. You can see there is a lot of signs of corrosion, and you can see that they have also tried to do the repair work, install some steel elements, structural steel sections over there, severe cracking here through the beams. So, I just want to show that, and this structure is not located in a coastal region. I just want to show that it is not just looking at the corrosion map which I showed earlier, corrosion map of India, where coastal region shows significant corrosive environment. You have to really look at the local exposure condition for the structure. Especially this one example is the chemical plants. Now, this is an example where in this particular structure they used chloride rich sand and chloride rich water. So, both sand and it could happen several places. It could happen that if the sea sand or some a sand which is rich in chlorides, if that is locally available, people will try to use it, but eventually you will see that it was not a good choice to do. We have to make sure that the ingredients which we use in concrete should be free from chlorides, or at least with minimal quantity. Now, and if you actually have chlorides within the concrete itself, like from the aggregates or from the water, you can even see corrosion within 5 years. This particular structure, it experienced corrosion in about just 5 years, 4 to 5 years they started seeing this problem. All these rebars which you see are severely corroded, and what you see here is there is some cathodic protection being applied, and whether we can protect the structure with cathodic protection. I will discuss more on that technique on a later date, later lecture, but I just wanted to mention that here. Now, when we talk, so we looked at different type of structures or the reasons for where is the source of chlorides, that is what we looked at. We looked at the marine conditions, or even it could be from the airborne chlorides, or could be from the materials used for making concrete itself. So, whatever be it, like if the chlorides are reaching the steel surface, what you will notice is that there will be something called pitting corrosion, or in other words, for example, here if you look carefully, then I have put this one of the arrow as in a thick line, thickness is more, indicating that this region might have more chloride than this region, and this will lead to an earlier onset of corrosion in this location. So, you may see that the corrosion, so like it is mentioned here, you can see a light pit there forming at an earlier time, because you have more chlorides reaching the steel surface over there at an earlier time, and this leads to pitting corrosion. I am going to show you how this happens in a different way. What is the chemistry of this chloride induced corrosion. So, if you have enough chloride reaching the steel surface, let us say you have enough chloride reaching the steel surface over, let us say here somehow you have chloride ions available, and they will try to react with the steel or iron over here, and these two will react and form ferrous chloride, which in presence of moisture will lead to formation of the rust, which is ferrous hydroxide, and also you have HCl formed. Basically, you create an acidic environment also there, and this HCl will precipitate again into 2H plus and Cl minus ions, which can attack the further steel, like another iron atoms it can attack, and then again it will form. So, this reaction will continue to happen, it will form more ferrous chloride, which again will in reaction with the moisture it will form HCl and ferrous hydroxide. So, this reaction, these 3 boxes, it will continue to happen, and so the point here is it is a catalytic reaction. So, once you have enough amount of chlorides to initiate this reaction, it is very difficult to stop it. Unless you can get rid of all the moisture in the concrete, it is very difficult to keep your structures very dry, especially when you talk about very large volume of the concrete elements. So, its best practice is to delay the time by which the chlorides can reach the steel. How can we do it? Either by increasing the impermeability of the concrete cover, that is the best way to do, or you can also go for the higher quality steel, which will result in the delayed initiation of corrosion. Now, let us look at how this pitting looks like in the case of a pre-stressing strand. You can see this is a picture showing the pits formed in a pre-stressing strand. So, if you look here very carefully, like in this cross section if I take, and this cross section if I take, or this cross section, the area available for taking the tensile stress is different, especially when you talk about this, the region with pit, there will be less area available, that means the structure may fail at an earlier time. So, this is more dangerous, it is not uniform corrosion. Even in the case of rebars, you can see there is a small pit here, there are more corrosion here, but less in this region, less in this region. So, there is a variation or spatial variation in the amount of corrosion happening, and so that is how we say pitting is happening when you talk about chloride induced corrosion. Now, earlier I mentioned that there is a parameter called chloride threshold by which determines the initiation of corrosion. Also there are other parameters which influence. I would mention here that this chloride threshold is not just a function of steel, it is also a function of the material in which you put the steel in. Anyway, before discussing that, let me show you how different the chloride threshold can be for different type of steel. These two are similar to typical steel which we use in the market, and this is steel. These two indicates that the chloride threshold for the stainless steel, SS indicates stainless steel, it is much higher than what it is for typical conventional steel reinforcement. And among the SS steels, you can see SS 316 has a higher chloride threshold than SS 304. But in India I do not think we use the stainless steel a lot unless we have a structure which you really want to have completely corrosion free, no risk at all, in taking where we do not want any risk of corrosion, we may go for stainless steel. And then there are other type of steels also available where they modify the microstructure a little bit, and which gives you higher chloride threshold than the conventional steels. So, point what I want to make here is, we must, when you talk about new type of steel which is coming to the market, we must check what is the chloride threshold, and we must also check the chloride threshold for the particular cementitious environment which you are going to use. And if it is low, there is one way of improving the chloride threshold is by using corrosion inhibiting admixtures. So, this picture you might, now it is probably familiar to you. You have a concrete and a steel embedded in it, and you have a passive film. So, this green patch indicates that passive film is formed. Now, these red dots over here indicates that when the corrosion inhibitors are used, we can make the passive film more dense or better passive film which will have more chloride resistance. So, the passive film formed on the steel surface when the corrosion inhibitors are used is much more protective or resistant against the chlorides. And typical corrosion inhibitor which is available in the market is bipolar corrosion inhibitor. Earlier it used to be anodic inhibitors, where it prevents basically forming a layer and it prevents the anodic reaction, but bipolar inhibitors actually helps in preventing both anodic and cathodic reaction from happening. And I am going to show you some results from our lab on the effect of corrosion inhibitors on the chloride threshold. First we looked at the effect of water cement ratio also. So, if you can see, this is 0.4 water cement ratio, you can very clearly see that when there is no corrosion inhibitors, that is 0 percentage, you can say the chloride threshold is around 0.3, that was the value which we observed. And when we added 0.5 percentage by weight of cement, you can see this is the percentage by weight of cement, it is written here. How much inhibitor concentration? There is an increase from an average chloride threshold is increasing from 0.3 to about 0.4, and when we put 1% corrosion inhibitor, it is further increasing average. But again I must say that there is one outlier probably here. So, at least we can say that there is an increase from this point. This is the when the case without the corrosion inhibitors, there is an increase. So, definitely the use of corrosion inhibitors seems to increase the chloride threshold. When we say it increases the chloride threshold, what it means is that the initiation phase which I showed earlier, like in the service life, the initiation phase it goes like this. So, this portion here in the service life chart, it is going to be more, this portion here is going to be more. So, the initiation phase can be enhanced or increased by using corrosion inhibitors. I will show you later how much it can be. And also when we go for a a higher water cement ratio, what we are seeing is there is no change in the chloride threshold. So, we have to really see that the effectiveness of these inhibitors are good when the water cement ratio is low. When the water cement ratio is high, they do not seem to really perform or to be of great use. So, this is a PDF indicating that probabilistic service life when we use corrosion inhibitors. So, you can look at these average values here where you can say 9.2 or about 10 years if you get when you do not use inhibitors. You can say that the inhibitors when we get about 20 years or 30 years. So, especially this one is for the bipolar inhibitor. So, 3 times increase in the chloride in the service life is possible by using bipolar type corrosion inhibitors. This was for the case with anodic inhibitors. So, anodic inhibitors, and this was for the case with bipolar inhibitors. Now, when we go for the inhibitors, earlier I showed results on corrosion properties. We can very clearly see that the corrosion resistance can be enhanced or chloride threshold is enhanced. However, if you do not have an optimum dosage or if we change the dosage, it can actually change the compressive strength and other durability, other transport properties of the concrete. I am going to show a little bit of that. So, you can see here this is the it indicates when there is no inhibitors used, you have about 40 MPa compressive strength. When the recommended dosage, RD stands for recommended dosage, we got similar compressive strength. Yeah, when we deviated from the recommended dosage by about -20, -40 and +20, +40, there is it is very clear that there is a reduction in the compressive strength. So, this thing must be considered while designing the concrete mix. So, you have to consider an optimum dosage which is able to provide corrosion resistance, and at the same time sufficient strength should be available. So, if necessary you can over design the concrete and make sure that the mix after the addition of the corrosion inhibitors is giving you right strength or desired strength. And other thing which these corrosion inhibitors can influence is the transport properties of the concrete. One example I am showing here is the Water Sorptivity Index. We saw that if you use this RD again recommended dosage, there could be an increase in the water sorptivity. That means moisture can ingress faster now into the concrete. So, all these have to be considered when we use corrosion inhibitors. It is not that you just take this chemical and mix it and it will give you everything what you want. So, what we have to look at is what is the right dosage for the corrosion inhibitor, when right dosage in terms of corrosion resistance, in terms of strength properties and in terms of transport properties of the concrete. So, all the 3 things must be considered when we choose a chemical corrosion inhibitor, and this is the same thing for all other chemicals also which we nowadays mix with concrete. Now, let me talk a little bit about the corrosion in cracked concrete. So, this is a schematic showing what different types of cracks which we would observe in concrete structures. Flexural cracks here, shear cracks here, this is also shear crack, and this is for a continuous beam element because the rebars are at the top here. So, these type of cracks it is possible to have in many concrete structures. Now, I want to show you some examples of different type of cracks in different type of elements. This is in a building where this actually what happened in this structure on the left side image is that they removed the formwork earlier that or before the concrete really attained the strength. So, I draw this black line here because it was very thin hairline crack, and so just to show you there was a crack like this on this beam. Now, imagine that there is a rebar which goes like this, and that rebar will have localized, will experience localized attack right when it crosses the crack. Now, another example of crack in roof elements is like this. You can see here, mostly sometimes then again here also it could be because of the removal of the formwork at an earlier time or because of the shrinkage of the concrete. Either thing can happen. You can see very clearly, like water, the scale formation, and it is just looks like all these here is scales. All these are scales, very clearly indicating that there is a passage available or a crack available within the concrete element, through which it can get the reinforcement inside can get attacked. Now, this is about on an example showing cracks in a highway bridge girder. It is actually a reinforced concrete bridge girder. You can see here very fine cracks. So, I am going to draw parallel to the crack, write one crack here, one crack here, another crack here, another crack here. So, and imagine now what will happen to the reinforcement which is going through these cracks. There will be localized attack in these locations, and that is what we should be really worried about. So, you can have crack going here also, you can have a severe localized corrosion attack at an earlier time. This is on a prestressed concrete girder, where again you can see a lot of shear cracks in this direction, and the schematic is showing very clearly how the shear cracks will look like. And in this particular structure you can see that it is actually the crack was filled with epoxy. You can see this brown color patch, it is actually filled with epoxy to prevent, but I do not know how effective this epoxy injection would be, because these structures undergo a lot of vibration. So, you have to ensure that oxygen molecules or water molecules cannot penetrate through these cracks. That is very, very difficult to achieve unless you really provide a proper cover. Instead of just filling the crack, we may want to go for a proper cover and covering layer. That might be probably a better option than just filling the crack with epoxy. Best thing is to prevent or do a better design so that these cracks do not occur. Now, this picture shows how carbonation can happen all along the crack. Very clearly, earlier we said if pH is greater than 9, then that means concrete is not carbonated. If it is less than 9, then the concrete is carbonated, which is indicated by this this region. This region very clearly we can see this is highly carbonated region, and now there is a crack here through which this carbon dioxide, it is reacting and then actually reacting in this direction too. Okay. So, what is the end result? You will have localized corrosion in this region. So, the steel in this region might experience localized corrosion. Similar is the case, it is not just carbon dioxide. If there is a crack, chlorides can penetrate through that, chlorides can penetrate through oxygen, moisture, all these can penetrate through these cracks, and it will attack the steel in a very localized manner, which is very dangerous when you talk about structural behavior. Now, we talked about the crack, and then there is something called crack width, which is how this problem is addressed in the structural design. As you see here, on the first column you can see different service conditions. If it is dry air or a protective membrane is provided, they allow a crack width up to about 0.4, and as you go down on the left side you will see that the condition is more and more severe or more corrosive in nature. Here you have seawater spray, wetting and drying, and continuous exposure to water, water retaining structures. So, as you go down the severity of the condition is more. So, we try to also reduce the allowable crack width or allowable or tolerable crack width, we reduce it, goes all the way up to 0.1 when you talk about water retaining structures. Now, so this is this crack width W here, it is the crack opening width over there. Now, if you have a structure like this, you can see the cover depth is here, and this there is a high tendency that this region will start corroding very, very fast. Now, what we can do is either work design the crack width and have a combination between crack width and the cover depth. So, if you have more cover depth, even for the same crack width, you may not have a condition where the crack is reaching the steel. There is no crack in this region, as you see here, no crack. So, this steel is better protected than this steel. The steel in the bottom image is better protected than the steel in the top image. So, point what I am telling here is that I am not telling to keep on increasing the cover depth, which of course, the structural designer has to look at. What I am saying is whatever is suggested in the design, we should ensure that that is actually implemented at the site, because sometimes we see that the cover depth, there is a significant variation in the cover depth. So, we must use proper measures on ensuring that the cover depth is adequately provided. Good quality chairs can be provided, but at the same time when I mention chair, the quality of the chair block should not be inferior to the quality of the concrete. So, it is very important to note down here. So, if you have proper cover, that is the best way to ensure durability of the structures. So, in summary, we looked at carbonation induced corrosion. We found that the carbonation process can reduce the pH of the concrete post solution, which will lead to uniform corrosion. That is a key feature we looked at, and there is something called critical pH threshold or critical pH at which is if about 9, if the concrete pH reaches about 9, then steel will start corroding. And the second mechanism we looked at was the chloride induced corrosion, which leads to localized pitting corrosion, and there is also a critical parameter which we call chloride threshold. The chloride threshold can be enhanced by using corrosion inhibitors, and also it is a function of both steel and the cementitious material used, not just the steel. So, and if there is a reduction, I mean you have to look at the how corrosion inhibitors, the dosage of the corrosion inhibitors used is also very important to consider. It should not affect the other properties of the concrete. For example, if you are using a corrosion inhibitor, you should ensure that its influence on corrosion resistance is more, but it should not influence the compressive strength or the transport parameters of the concrete, or in other words, even if it is influencing, we should take adequate measures as a design during the design process itself. Now, cracks can accelerate the ingress of deleterious elements through the crack. Chloride, carbon dioxide, oxygen, moisture, all these can penetrate and reach the steel surface at an earlier time, which will lead to localized corrosion. I think with that we will stop this lecture. We will look at in the next lecture we will look at different type of steel reinforcement available and what are the precautions to be taken when we use those kind of advanced steel reinforcement which claim better corrosion resistance.